Hi, everyone. It's a pleasure today for the Barcelona Economic Society to host Professor Esteban Rossi-Hansberg from the University of Chicago. Professor Rossi-Hansberg is a specialist in international economics, regional and urban economics, as well as growth and organizational economics. We can add to that list, of course, climate change economics. We've already hosted some of his co-authors, Adrian Bilal and Paul Antras, and we're very excited to have to have him today with us to share some of his research, which I've already had the opportunity to look at some of his output. He's got a very cool world map. Which I recommend you check out. And as we said, that work is fundamental for what we're going to talk about today. So if you are really interested about this, I think it's a really cool project that I recommend you check out. So Professor Rossi-Hansberg, of course, is a renowned researcher who has received numerous awards for his work. He's now currently the lead editor of the Journal of Political Economy. And he's also a research fellow at the CPR and at the NBER. So thank you, Professor Rossi-Hansberg, for being today with us, and the floor is yours.
All right, thanks for having me. So today I want to talk about climate tipping points and the way this connects with some of the work that we've been doing on climate change, which is about trying to understand what the impact of climate change will be on the economy of the world, and in particular the part of that we've emphasized and that we focused on is the idea that, as climate change develops, that's going to affect different parts of the world differently, and that how much these different parts of the world are going to be affected depends importantly on spatial links, depends importantly on the trading relationships between locations. It depends importantly on, the ability of people to move across space. It depends importantly on, how much the different regions invest and innovate in terms of improving their technology. And so we've generated models with kind of a lot of spatial detail to try to do this evaluation over time and think about, how climate change is going to affect the economy today and in the future across different parts of the world. And so, every time I've talked about this work and presented this work, one of the very common questions that people will ask is, well, but what about, you're looking at some scenarios, but what about tipping points, right? What about the fact that the economy at some point can, or the climate system of the world can at some point be, reach some form of tipping point that then is going to unravel other types of consequences that perhaps we're not considering, or that may be more extreme than the scenarios that we're considering, and so on. And so this work that I'm going to talk about today is kind of, in some sense, the response to some of that those concerns. And so what we're going to do specifically is think about one tipping point, which is what is usually referred to as the Atlantic meridional of returning circulation. That's kind of a mouthful. I'm going to call it AMOC from now on. And what it is the fact that there's a system of currents in the Atlantic Ocean that brings water, which brings heat from the south to the northern part of the world, and in particular, it warms Europe, and so it increases the temperature in parts of Europe and makes the temperature much more even over the year, and so it makes it more stable. And so this is kind of important. It's an important part of the climate system because it, in some sense, reshuffles heat from the southern seas to the north of the globe, particularly in the kind of in the Atlantic region. Okay, and so one of the concerns here is that that process, that circulation, is going to stop or is going to slow down significantly in response to climate change, to the world warming up. And so we want to kind of try to understand what would be the economic impact of such a slowdown of that circulation system. Okay, and so the first thing I'll talk about a little bit about is explain kind of the the ABC, the very basic climate aspect of this circulation, and why would it stop in response to climate change, and then I'll do the economic evaluation. So this is a diagram that kind of shows this. It shows how, in blue, that's the circulation that goes from the north to the south, and then there's warm waters, that's the red lines that come from the south to the north, and in particular warms this part of Europe as warm waters come into that region. And the way it works is essentially it's like a pump. It circulates the water by bringing water from the south. As I said, that water is because it comes from warmer regions of the world, it evaporates, and so it comes with a relatively high salinity, so it has a lot of salt in it, and so as it comes to the north, that salty water gets cooler because of colder temperatures, and cool water sinks because it's denser than other forms, than the water that has less salinity and is warmer, and so it sinks, and that process of that water sinking acts like a pump, and so that essentially makes that water sink at the bottom of the ocean. That makes water flow, or cold water flow, to the south, and that makes the water circulate from the south to the north, as I showed in this previous map. And so that acts as a conveyor belt, essentially, where you have this pump where water is sinking because it's salty and cold, right? Now, what happens with climate change? It can weaken because the water that comes with the salinity, right, that makes it dense, and that we said, well, it's going to cool down, and then cold, salty water sinks. Well, if with climate change it's going to get less cold as it comes to the north, and so that is going to imply that it's going to sink less, or it's going to be less dense on one hand. And then the other important aspect of this is that, with climate change, icebergs are melting. That's kind of sweet water that mixes now with this water that is coming from the north, from the south, and so that implies that the salinity is also going down. And so all those two things, the fact that it gets less cold and the fact that it's now mixed with water that it has less salt in it, implies that it's less dense, and as a result of that sinks less, and so that kind of stops that pump, if you will. Okay, and so what is the danger, or the potential collapse, or the tipping point, if you will, is the fact that as that water becomes less salty and less cold, that pump is going to stop working, is going to be less powerful in making that water sink, and therefore create the circulation. And as it starts weakening, less water is coming, and so that implies that less salty water is coming to the north, and so that implies that it keeps weakening until potentially it can collapse. And that can take many years. It can take up to a century for that to happen. So it's not a tipping point in the sense that something dramatic will happen when we reach that tipping point. But the tipping point part is the fact that once it starts weakening, it's going to continue to weaken. Once you tip it, then it's going to get weaker and weaker over time. And it's going to take a long time to really kind of go away, but or weaken all the way to stop. But there's very little we can do once it starts weakening. And so, in some sense, once it starts weakening, we know that this will happen. This will happen, okay, in the future. And scientists have been studying this for a long time. There's a lot of studies that tell us, what are going to be the kind of the climate, what's going to be the climate impact of potential collapses of a mock, how long it will take, and so on. And so I've written here some of the literature that tells us, when this will happen. And so, the IPCC, I guess, which is what kind of one standard source for knowledge on this, is that it's going to weaken between 4% and 55% by 2100, with some kind of not super high probability, but some probability. And then the main kind of study is this Van Vesten et al. Study in 2025, which is kind of a survey, if you will, or putting many, it's not a survey, but it puts many climate models together to try to get kind of some sort of consensus view about what the impact of this will be. And that kind of concludes that it's going to start collapsing maybe by 2063 on one of the RCP scenarios. These RCP scenarios is, think about it as like the scenarios about the evolution of the economy, and then depending on the different scenarios about the evolution of the economy, in particular kind of carbon emissions in the economy, you can make predictions about what's going to happen. And so RCP 4.5 is kind of an average scenario. RCP 8.5 is a more extreme scenario, where, which is normally referred to as business as usual. If we keep emitting carbon into the air, and so climate change happens at a faster rate, then what they conclude is that maybe, this is going to start collapsing in 2055. And so then, this is more imminent. Why? If you take that seriously, then, this is something that we probably should kind of start worrying about now. Okay, and the world, in some sense, has already started worrying about it. I have here a bunch of different newspaper headlines from the Financial Times, the Daily Express, the Economist, and so on, that kind of make very dramatic statements about what could happen in different parts of the world, and in particular in Europe, right? It's particularly potentially problematic, or according to these newspaper articles, for Europe. But these are newspaper articles or magazine articles, and so they don't do like a full economic evaluation of its impact, which is kind of what we're up to. Okay, so what we're gonna do then is gonna develop a model which is gonna borrow from what we've done in the past. We develop a model of the world economy over time at a fine level of spatial resolution, in particular at 1 degree by 1 degree level of resolution in the world economy. I'll show you a bunch of maps that kind of show that, and then think about incorporating a mock into these models to evaluate its consequences. And so, I'm not going to go into all the details of the model because we don't have time to go over all of that. But let me give you kind of the basic structure of the model. And so this is a model that is based on the work, some of the work that I have with Jose Luis Cruz, and in the Review of Economic Studies. And there we kind of propose a model to evaluate climate change with this spatial detail that can be described kind of through with this diagram. So think about the economic component of the model as the black part in the diagram. And so there's going to be individuals and firms that are going to locate in these 1 degree by 1 degree cells in the world, throughout the world. There's about 17,000 of those with some land in them. So we're going to consider all of them. And there's going to be people there. There's going to be firms there. The people are going to work. They're going to consume goods that they either produce themselves or that they import, subject to some transport cost or trade costs from other parts of the world, and they're gonna supply land and labor to firms to produce, and we're gonna give them the ability to migrate across across locations. So if they want to leave a particular location, say because climate change makes it worse, they are going to be able to move. It's going to be costly for them to do so, but they have the ability to do so. And then on the other hand, there's firms. These firms are going to produce. They're going to trade goods with other regions, again, subject to transport costs. And then we're going to give them the ability to innovate and improve their technology by spending some resources in doing so. And so that is going to imply that productivity in the different locations is going to be endogenous to whatever is happening in the economy, including the potential effect from climate change. And so these firms are then going to pay wages for labor, rents for land, and which agents are going to use to then buy their consumption basket. And so agents are going to use that consumption, or are going to consume goods depending on how much they earn in that location, and that together with the amenities of the location, how attractive is the location as a place to live, then they're going to decide where they want to live. Okay, so they're going to decide where to go in terms of what location to live in. And so that's the economic component of the model. And so think about agents deciding, how much to buy from the different locations, where to live, and in what part of the world to live. And then firms at the same time, depending on all those choices, they're also deciding how much to produce and how much to innovate. Okay, and so that's happening, and that's evolving over time as firms innovate and productivities evolve. And so that's going to give us some sort of path of the distribution of economic activity in the world over time. And so to that basic core model, which is kind of a core model that we have in a paper in the JP with Klaus Desmet and David Nagy, that core of the economic model comes from that. What Jose Luis and I did is we add like a climate structure to that. And so, now we say, well, energy is going to be an input in production too, and that energy in turn can be produced using clean sources or fossil fuel sources. To the extent that it uses fossil fuel sources, that's going to generate CO2 emissions. Those CO2 emissions are going to affect the stock of CO2 in the atmosphere. That in turn is going to imply changes in global temperatures, and these changes in global temperatures then are going to affect local temperatures. And it's these local temperatures that in turn affect the productivities in the different locations, the amenities in the different locations, and birth rates in the different locations, or birth minus death rates. So in particular, they may affect mortality, because we know that climate change can affect local mortality rates. Okay, so that's kind of the model in a nutshell. You can specify it. If I go to the specific equations, etc., you can think about like some period utility of an agent that lives in location R, has some history of it where it has been, that is given by R bar minus there. And it's an individual agent I at time t. It consumes a basket of goods that is aggregated CS, and those goods come from the different parts of the world. It has some amenities, some level of utility for living in that location, and then some idiosyncratic component for living in that location, which is like, whether you like it for some, specific reasons to you or your history or your family, why that you like that location in particular. And so that's going to be distributed in some way. And then we have the moving cost. So if you move from a particular location to another, you're gonna pay moving costs associated to that move. And we're gonna put a lot of structure on those moving costs that is gonna allow us to solve this model kind of in a simple way. And that's kind of the work that we've done in the past to show that that kind of works well and simplifies the models in ways that allow us to have all this spatial heterogeneity. Okay, and so the reason I mark this B in green is that that's where climate is going to affect the economy, or one of the ways in which climate is going to affect the economy. So this B is in turn determined by B bar and some congestion force that depends on the number of people that are in that location. And then which is given by L, and then this B bar, that's where climate comes in, depends on the B bar in the past, and it's affected by climate, which is this term here. And so what does it mean? It means, well, it's going to be affected by what I'm going to call this damage function in amenities, which is going to depend on the change in the local temperature in that location. Is also going to depend on the level of temperature, but in particular, it depends on the change in the local temperature. And so if, for example, a location that is already very warm gets even warmer, right, that's not good for people in that location. They don't like it, right? And because it's not as nice to live in that location. Okay, so that's the type of effects that's supposed to capture. But these damage functions are essential. That's the way the climate system affects the local economy. So I'll talk more about that. So now let's look at the production side. So think about a firm, think about production per unit of land. That firm is gonna, innovate, improve its technology. It's gonna have some idiosyncratic productivity from, producing to produce in that location. Then it's gonna hire some labor to produce. It's gonna hire some energy, and everything is per unit of land. So therefore, this is kind of decreasing returns in labor and energy, which is given by the fact that mu is less than 1. And so because land is an input in production and land in a location is fixed, that's going to be a source of a congestion in this model. Okay, and then these productivity Z's, they're going to come from some distribution that is going to have mean governed by this A variable. And so you can think about this A variable as the level of technology in that particular location, which we're going to allow for some agglomeration effects that again depend on the total number of people in that location. But then the evolution of that A is going to depend on how much firms decide to innovate, but also it's going to depend on the climate. And so there's another damage function. This is a different damage function than the previous one I showed you. This is for productivity, right? And this damage function also is going to depend on the change in the local temperature. And so this is about the fact that, if the local temperature, say, increases and the region is already pretty warm, then that's going to affect negatively, the ability to produce in that location. Okay, and so we're going to add some other effects, some dispersion effects, etc., that I'm not gonna, explain or talk about in that much detail. Okay, and so think about firms, and so firms are gonna face this technology, they're gonna optimize, they're gonna hire all their inputs, and then, like I said, they're gonna trade with other regions subject to trade costs. And so this is what's called in this literature like a gravity model, where trade is going to depend on the relative size of the different regions and the transport cost or trade cost between the different regions. And then finally, we have like the energy mix, or how this energy that was an input in the production of the firm, how is that determined? Well, it's going to determine, like I said before, using fossil fuels and clean sources. And they're gonna be aggregated using like a CS type of aggregation with some elasticity of substitution. And this elasticity is kind of important in the sense that it tells you how much are you willing to substitute fossil fuel sources for clean sources. And so you, for example, as the cost of fossil fuel sources increases, because, say, we run out of oil or we run out of gas, we're going to substitute naturally away from fossil fuels into clean sources. And so we're going to allow for that. And that process is going to be governed by that elasticity epsilon that we have in that equation, right? And then on top of that, there's a climate system. And so, depending on what type of fossil fuel the different firms use, that's going to lead to, like I said before, global emissions. And those global emissions are going to affect temperatures. And that process from the economy to, global temperatures and then to local temperatures, we're essentially borrowing from the, scientific literature. Okay, and so that's what's called the carbon cycle, and we're gonna use the carbon cycle that is standard in this climate literature. And then the key thing, and like I said, or the key object that we need to discuss is these damage functions. How are we gonna obtain these damage functions? And so we can quantify all these models. And the key to this quantification is that we can, use. We need data on population and output in the different locations in order to invert the model and obtain both amenities and productivities in each one of these cells. And then if we have that over time too, we can use that to identify migration costs. And if on top of that we have trade flows across locations, or if we have the transport cost across locations, we can also quantify that to make sure that we match the trade flows properly. And so we're going to do all of that. And so that's going to give us a model that in the baseline year, which in this case is going to be 2021, the model is going to exactly match the economy as we see it in that year. Okay, so in some sense, the model has enough flexibility to exactly match the economy at that level of disaggregation in the baseline scenario. And then we're going to simulate the model forward over the next couple of centuries to see kind of what the potential effect of AMOC is going to be in the future. And we're going to introduce climate change just through the standard carbon cycle effects on temperatures, but also like AMOC, which was the whole point, right? And so the way we're going to do that is we're going to take that study that I mentioned before and say, well, that study tells us that when world temperatures kind of hit around 3 degrees Celsius on top of current levels, then that's going to trigger the start of the decline of this current system. And then once it starts, we're going to allow it to decrease by 80% over the next century. Okay, so that's going to give us some sort of slow impact of the effect. And this study by Van Vesten and all tells us, look, if AMOC collapses, this is the marginal effect that's going to have on temperatures in the different parts of the world. And so we can use that and incorporate it into our analysis. Okay? Now, as I mentioned before, two key aspects of this are these damage functions, right? The fact that how is it that changes in temperature in a given location affect amenities on one hand and productivities on the other in that location. And so for that, in that paper with Jose Luis Cruz, we estimated these damage functions using kind of local variation in temperatures over time and across cells with different temperatures. And so this is kind of the outcome of that, which in the x-axis you have the winter temperatures in or either July or January, depending on what part of the hemisphere you are, in the different cells, right? And so, you go from the coldest ones to the warmer ones. And what this is telling you is, well, if temperature increases by 1 degree Celsius in that cell, by how much do amenities increase in that location? Okay, so that's what this is, like a semi-elasticity of temperature and amenities. And so that gives you, that this would tell you is, well, if in the coldest places in the world, when temperatures increase by 1 degree Celsius, amenities increase by, say, about 2%. Okay, so that's or 2.5%. That's what that's saying. And as temperatures, as we go to cells that have baseline temperature, winter temperatures that are larger, this kind of comes down. Eventually, you hit zero here, and then as go warmer and warmer, the effect on amenities reverses. And then, in the warmest place in the world, an extra degree Celsius is actually bad for amenity, right? People don't like it. Okay, so that's one of the damage functions, that the damage functions on amenities, and there's kind of a similar one for productivities that, again, it has the same logic. And you can see, there's kind of clearly standard errors around these estimates and so on. So that tells you, there's only, where we know something about this, but we're also relatively uncertain about the magnitudes of those effects, particularly when we're kind of close to temperatures where baseline temperatures, where changes in where we're kind of close to the optimal temperatures, and therefore changes in temperatures have little impact on either amenities or productivity. So you see the standard errors there are kind of quite big. But still, what's nice about this is that it very clearly shows that in the coldest places in the world, increases in temperature are a good thing, right? They increase both amenities and productivity. So if you're in a very cold place, having temperatures increasing is good for you, both on the amenity side and the productivity side. But if you're in the warmest places in the world, right, higher temperatures are going to lower your amenities and are going to lower your productivities, right? And this is not imposed at all. This is all coming in response to, this is just estimated, right? And so it comes out of the estimation. This is fully non-parametric. So, we're just, the data is telling us that that's the case, okay? All right. So now let's talk about AMOC itself. So what this Van Vesten et al. Paper tells us is these are going to be the changes in temperature if AMOC collapses under this RCP 4.5 scenario. Okay, and look at this. I mean, this is pretty dramatic. The left map and the right map are showing the same data. The only difference between them is that I restricted the range in the one on the right so that you could see a little bit more detail. Okay, so in the one on the left, I didn't restrict the range. I mean, I restricted, but I made it very large. And so there you can see that, in some of these northern latitudes, right, temperatures are going to collapse by, according to this, 25 degrees Celsius. So that's like a huge, huge, huge effect, right? So if AMOC collapses, those places that I just, that I marked, these places here, right, are going to really, really get a lot colder. And so that's a very negative effect. When we look at the world overall, right, the marginal effect of AMOC, you can see that, all these places are going to get very cold. Now I'm restricting the range to -4 to 4 degrees Celsius, right? But, some of these places in the south are going to get warmer. Why? Because, you're stopping the circulation, right? So there was, cool water coming to the south through the circulation too, and so that's not happening anymore. And so that means that some of these places here are getting warmer as well. But look at how widespread is the cooling down. So we have like sub-Saharan Africa here, etc., parts of the Sahara also getting cooler, parts of North America. You guys are in Spain. I'll show you more detail on that later on. But that's gonna get cooler if this happens as well, right? Not a lot. We're still in this range of -4 degrees and +4 degrees, but this is the scientists are telling us this, right? This is we haven't done anything to generate these maps. This is just reading the data from them. Now we want to incorporate this data into our model. And so what I'm going to do is I'm going to bring that in, bring that threshold that once we reach the 3%, 3 degrees Celsius threshold, the amok is going to start collapsing. It's going to collapse, like I said, for the next 80 years or 100 years, sorry, by 80%. Okay, and so if I bring that in, I'm gonna have some predictions. Before I actually bring that in, let me show you what this model implies as a baseline. So still without amok, right? Still without the amok collapse. So absent the amok collapse, this is the baseline. So focus on the top row, right? So this is by year 2100. This is in year 2200. What is the effect? What is the effect of global warming? And so what I do is I simulate them all with global warming, then I simulate them all without global warming, and this is the ratio of outcomes by 2100 in terms of welfare. Okay, so I'm showing you the welfare. And so what is this telling you? It's telling you, kind of what we know from this other work, etc., that climate change is going to be really bad in, parts of Africa, parts of South America, India, and so on. It's going to be good for parts of northern Canada and parts of Russia. And then, in the rich world, it's going to not be the rich world is going to be kind of less affected, right? And once we reach 2100, we are kind of pretty much there. The effects kind of keep accumulating a little bit over the following century, but not that much. Here, I have a range of 10% plus and 10% minus. So that's why you see kind of these colors bump up a little bit. And the reason I did that is so that you can also see RCP 4.5 on the same scale. And so, those effects are much milder. You see some effects by 2100 there that have essentially the same pattern. And then by 2200, kind of some of this kind of reverses because we stop using fossil fuels, because fossil fuels get a little bit more expensive relative to clean energy. And so, compared to today, right, or not today, but 2021, the effects are much smaller, as you can see. Okay, so this is kind of a relatively mild scenario compared to now. Now, people sometimes compare to pre-industrial temperatures, and so then of course the effects would be larger because we already had like 1.5 degrees extra global temperatures, right? So this is already kind of in some sense factored in this graph. So this is just to give you the baseline, how this baseline looks, right? Now I'm gonna bring in amok, and the first thing I'm gonna show you is, well, what is the effect of amok collapse, right? So now I'm gonna allow for that to happen relative to the global warming, but without the amok collapse, right? So if we forget about the amok collapse, what is the marginal effect of incorporating the amok collapse relative to not incorporating? Okay, and the point of this graph is, you don't need to look at it very carefully, but I mean, the impressionistic look should be, well, this looks just exactly the opposite as the previous map that I showed you, right? The red is in places where, here's the previous map, right? Just to remind you, so blue in Africa, blue in India, blue in South America, red in the north, and here is exactly the reverse, right? And so what is this telling you? It's telling you, look, the marginal effect of the amok collapse is gonna be is gonna affect the places that are most negatively affected by climate change in a positive way, right? So it's kind of reversing, in some sense, some of the traditional effect of climate change, which I showed you in the baseline. So the fact that these maps kind of are the inverse of each other tells you that. Another way of seeing the same thing is this graph. So this graph shows you that, so what I have on the x-axis here is the baseline effect from climate change, so warming relative to no warming. And this is amok relative to an economy with warming, so the marginal effect of amok. And so what you can see is kind of there's a very clear negative relationship here. Every point is one of these cells. The size of the cell, the size of the circle is the population of that cell in 2023. And you can see the negative relationship that forms, meaning the places that are very negatively affected by climate change are actually positively affected by the collapse of amok. These are these places, right? And then the places that are very negatively or positively, affected by climate change, they are negatively affected by amok. So those are some of these places here. And so here on the one on the graph on the right, what I have is this just like a zoom in, if you will, for Europe, right? And so here you have what's all of this? These are all these small areas in Russia that don't have a lot of people. That's why the circles are so small. But are going to be positively affected by climate change on average, but negatively affected by amok because amok is cooling them back. Okay, and so you have this very strong negative relationship, and as you can see, it's not perfect, right? There's variation, but the relative pattern is amok is kind of reversing some of this impact of climate change. Let me skip through that. And then I can also show it to you in a different way. Suppose this was about the marginal effect of incorporating amok, but what if I say, well, I don't care about the marginal effect of incorporating amok. Now I care about the whole thing together, right? So I'm going to compare no warming and then the complete model with climate change and amok, so everything in, right? Then you get these results that I'm showing you here. And these results we think are pretty dramatic in the sense that they really change the picture of the effect of climate change, right? Because now, what you see is that, yes, there's still a negative effect of climate change in this area, which was kind of is the traditional effect. But now you also have kind of negative effects kind of in Northern Europe, parts of Northern Canada, and you only get effects in kind of these very northern parts of Russia and Alaska and Northern Canada. Okay, so now you shifted the cost of climate change to this part of the in particular to northern Europe to a large extent, and that kind of in some sense kind of reverses the impact exactly because of this effect. And so because you're kind of reversing the impact from climate change with amok, that now implies that more of these regions are losing. Now, and so if we go to the milder scenario, the 4.5 scenario, look at what happens. What happens is that most of these regions now are losing. There's very few gainers by 2100, and then in the very long run, relative to today, again, what you have is that some of these places here can actually benefit from climate change relative to today. They were already hurt from pre-industrial levels to today, but relative to today, they may actually improve because the temperatures kind of plateau, and then here comes amok, and amok kind of actually makes them relatively cooler than they are today. And so that kind of really changes completely or turns on its head the map of the effects of climate change that we normally see. Okay. And so I am running out of time, but kind of in my last 5 minutes before I kind of see if there's some questions or comments. One of the things that we also do is kind of focus a little bit more on Europe. As I showed you, kind of some of the big implications are going to come from Northern Europe and the fact that Northern Europe is going to cool significantly if amok collapses. And so I can zoom into that and show you kind of a little bit of the local effects. And so what I have here is first the welfare ratio of the marginal effect of amok. So the marginal effect condition where I have warming in both cases, and I'm just have amok in one and not in the other. And so what you can see is that the effect of amok is bad for certainly for northern Europe here, in particular Scandinavia and parts of the UK, parts of Central Europe in the more mild scenario, but in the more extreme scenario where temperatures are actually warmer, then ammox actually helps most of Europe. Still not Scandinavia because the effects on cooling are very extreme there, but in other parts of Europe, climate change is going to be negative, and so what the amok just takes away some of those effects, right? It cools it down relative to what you would have, and so in that sense, it's actually a good thing for Europe, particularly in the more extreme scenarios. And you can break this down by productivity or GDP per capita. All of it kind of shows similar patterns. You can look at population, which is going to move to some of those areas in southern Europe relative to parts of northern Europe. And so the AMOC is kind of important also to think about the reallocation of population across parts of Europe. And so there, Spain, Italy, parts of France are going to be the winners relative to parts of northern Europe, and that's mostly coming from these effects on productivity on one hand and amenities on the other. And so ultimately the point is that we have this potential shock on this tipping point, climate change. Now, if it unravels that, it's going to have kind of different implications in terms of what regions gain and what regions lose. And some of these implications and to calculate and to estimate these implications, you really need these spatial frameworks that allow for population mobility across locations. And here you can see it, how, what's the change in population in response to the effect of, incorporating amok here. And some of these changes in population are quite significant. So, you have about a decline in Europe, excluding Russia, of about 8% in population by 2200 under a scenario that is relatively mild. In fact, for the more extreme scenarios, the effects in one population are actually a little smaller, and then that results in kind of also relatively large effects on GDP from incorporating amok. And so in order to get that effect, to calculate the actual impact that you're going to have from this phenomenon, you really need to incorporate some of these links across locations. And so that's what this work is trying to do and trying to propose in terms of frameworks. Okay, and so that's pretty much all I have. And so the point of this is to show you some of the impact of these tipping points, the impacts of climate change more generally, but also to kind of encourage you and to, when you think about these frameworks, to really think about not only climate change is bad or what's kind of the general effects that climate change is going to have on the world economy, but also to think kind of in a little bit more detail about what are the trade-offs and what are the adaptation mechanisms that the economy can have, and how those are going to play a role in the overall impact that this is going to have across regions in the world. So let me stop there, and happy to answer anything if there are any questions.
Thank you, Professor. If anyone has a question, you can unmute yourselves and ask it, or write it on the chat if that's better for you, and I'll read it aloud. So let's wait a couple of minutes.
I had a question. Can you guys see me?
Yeah, we can see you, Marty.
Yeah, perfect. Yeah, I had a question. One of my ideas is, well, we have this situation which in the future will generate perhaps inequality in those areas that are more affected by a mock, and those who would more like positively, and some others will be negatively affected. I wanted to know if you have tried to introduce transfers, because the maybe the if we kind of reallocate those welfare effects in the future, there could be like a possibility of mitigating the effects of amok global warming. Have you considered how organizations, perhaps like the IMF or organizations that lend money to countries, and international transfers, how they could perhaps mitigate the effects of global warming, or do you think it's not substantial to the discussion?
I think that there's many different types of policies that we can consider, and I think transfers are certainly one of them in terms of trying to help some of the people that are affected by this. I think the key issue with transfers is that what you don't want to do, and I think these frameworks are particularly good at highlighting this, is because you want to kind of diminish or reduce some of the impact of climate change in particular regions, you generate these transfers, and then in response to these transfers, people decide not to adapt to climate change, right? And so what you want is to allow them to adapt, and then maybe help that transition and help you know make sure that they are, to reduce suffering or the suffering that could result from some of these shocks. So you want to be humanitarian for sure, but at the same time, you want to be very careful not to change the incentives to adapt. Okay,
Mm,
and
right.
and in some sense, what this highlights a lot is we want to be very careful with that. And so, the standard example of this is, you can subsidize insurance against some of these shocks. And so the standard thing is like subsidize, flooding insurance or hurricane insurance, or have the government come in. And then what happens, people stay in those areas, even though we kind of know that those areas have high probability of being affected, right? And so in
Mhm.
some sense,
Right.
we want to combine policy that is humanitarian on one hand, but also is careful not to destroy the necessary incentives for people to adapt by moving across locations. And so,
Right.
because that's a very powerful and important form of adaptation.
All right. Thank you.
All right.
Any more questions?
All right.
Well,
Thank you.
exactly. If there are any more questions, we'll leave it here. Thank you, Professor. It's been a pleasure hosting you, and thank you for your time.
Thank you. And it's a pleasure.
Goodbye. Have a good weekend, everyone. Thank you.
Thank you.